in the quiet shadows of a dimly lit study where rain lashes against a shattered window. A fallen whiskey glass reveals an invisible truth on its curved edge. A faint smudge of sebum and sweat, undetectable to the naked eye, transforms under magnetic powder into a landscape of ridges and valleys. This is no ordinary mark. It is a biological signature, forged deep in the womb, that can tie a single individual to one precise moment in time with absolute certainty. Yet what if the very pattern that defines your identity was never fully written by your genes alone? What if a hidden world of chaos and chemistry, unfolding before you even drew your first breath, made every fingerprint on Earth truly unrepeatable? That question opens a door to one of the most remarkable processes in human development. The mathematical odds of any two people sharing identical fingerprints stand at roughly 1 in 64 billion. Consider that only about 117 billion humans have ever lived across all of history. Your fingertips represent a cosmic lottery won at the moment of conception. A personalized map so distinctive that it has powered forensic science for more than a century. Recent advancements in artificial intelligence have taken this uniqueness even further. They demonstrate that the precise orientation of microscopic features makes each finger on your own hand as distinct from the others as it is from any other person alive. Picture yourself at a crime scene, where investigators dust for prints and instantly narrow their search. This is the practical power of fingerprints, delivered with clinical precision in every courtroom and border checkpoint around the globe. But behind that straightforward fact lies a deeper story. One that begins not in adulthood but in the fluid gravity of the uterus. Around the 7th week of gestation, smooth mounds known as volar pads emerge on the developing fingertips. These tiny cushions serve as the geometric architects of destiny. Their height and tilt determine the broad design that will follow. A flat pad lays the groundwork for a simple arch. A tilted one produces a flowing loop. And a highly elevated, centered pad gives rise to the intricate spiral of a whorl. The process accelerates dramatically by the 10th week. The basal layer of the epidermis, sandwiched between the outer skin and the deeper dermis, erupts in a ferocious burst of cell growth. This rapid expansion creates immense compressive stress, much like the buckling of the Earth's crust during a tectonic collision. The tissue folds inward, carving out the primary ridges that will define the visible pattern. This mechanical event does not happen in isolation. It is guided by a precise chemical symphony known as the reaction-diffusion system. A concept first theorized by mathematician Alan Turing in 1952. 3 key molecules engage in a microscopic battle for control. The protein known as WNT stimulates the upward growth of ridges. Its counterpart, BMP, acts as a suppressor to carve out the intervening valleys. Meanwhile, the EDAR gene orchestrates the spacing and density of these waves. These chemical signals do not radiate from a single point. They erupt simultaneously from 3 distinct epicenters: the apex of the fingertip pad, the crease at the first joint, and the center beneath the developing nail bed. Imagine dropping 3 stones into a still pool at different moments. The expanding ripples collide and interfere, twisting and buckling to create a turbulent mosaic. This collision ensures complexity. It prevents any 2 fingerprints in human history from ever matching perfectly. The environment inside the womb adds yet another layer of individuality. Even identical twins, who share the exact same genetic code, develop distinct prints. Fluctuations in amniotic fluid pressure, subtle shifts in maternal blood flow, and the random angle at which a tiny finger brushes against the uterine wall introduce what scientists call physical noise. These stochastic variables act like an improvisational jazz musician playing alongside the written notes of the genome. They force ridges to terminate abruptly or split into branches, producing the microscopic intersections known as minutiae. An average fingertip contains between 75 and 175 of these points, each one a unique fork, ending, or isolated ridge. By the 19th week of gestation, the construction phase ends. The pattern locks permanently into the basal layer through specialized molecular anchors called desmosomes. These biological rivets hold the architecture in place like deep foundations beneath a building. As the child grows, the skin stretches, but the core geography of loops, whorls, and arches remains unchanged, even if the surface skin suffers a minor burn or scrape. The basal layer functions as a memory bank. Regenerating cells rise faithfully from below, reconstructing the exact same ridges. Only a catastrophic injury that completely destroys this deep layer can replace the intricate labyrinth with featureless scar tissue. This remarkable regenerative capacity explains why fingerprints remain reliable throughout a lifetime. They withstand daily wear from gripping tools, typing on keyboards, or shaking hands in countless interactions. The system evolved as a practical adaptation, yet its true beauty lies in the balance between genetic instruction and environmental improvisation. The final pattern is never a rigid copy of DNA. It is a localized rebellion against pure genetic determinism, shaped instead by the unpredictable pressures of a dark, watery world. But the story does not end with the vast majority who develop these intricate maps. In exceedingly rare cases, a mutation in the SMARCAD1 gene halts the entire process. This condition, known as adermatoglyphia, leaves the fingertips as smooth as polished glass. Sometimes called immigration delay disease because it complicates international travel and identification. It affects only a handful of families worldwide. The same genetic change that prevents ridge formation also disrupts sweat gland function in some individuals, creating a dual absence that underscores how interconnected the skin's structures truly are. Those born with this trait exist as living proof of what happens when the delicate balance of physical buckling and chemical diffusion is erased from the developmental script. They remind us that fingerprints are not inevitable but the product of an exquisitely timed symphony. And yet, even this rare exception illuminates a larger truth about human identity. Fingerprints are far more than forensic tools. They represent the first tangible record of our individuality, etched long before conscious thought or personal choice. They carry echoes of the chemical wars and silent movements that occurred in the womb. Every loop preserves the memory of a microscopic collision. Every branching minutiae captures the exact pressure of amniotic tides. This topography, engineered to last a lifetime, connects each person to the fundamental forces of biology, physics, and chance. The implications extend beyond personal uniqueness. In medicine, understanding this process opens pathways to therapies for congenital skin disorders. Researchers continue to explore how manipulating these same signaling molecules could one day help regenerate damaged tissue or address conditions related to abnormal skin development. In forensics and security, the reliability of these patterns underpins global systems of identification, from criminal investigations to border control. Yet the deeper value may be philosophical. In an age when technology increasingly blurs the lines between individuals through data and algorithms, fingerprints stand as a quiet affirmation that true uniqueness begins at the cellular level. What emerges from this journey through embryonic development is a profound appreciation for the hidden craftsmanship of life. The ridges on your fingertips are microscopic monuments to a subterranean collision of forces. A frozen record of the shifting pressures in a protected aquatic realm. They endure until the body itself returns to dust, serving as both practical identifier and biological wonder. Scientists and researchers who have dedicated their careers to unraveling these mechanisms deserve our deepest respect. Their meticulous work, from early observations of volar pad geometry to the latest molecular studies confirming the reaction-diffusion system, has illuminated a process once shrouded in mystery. Through their efforts, humanity gains not only practical knowledge but also a richer understanding of the intricate beauty encoded within every person. Their contributions continue to expand the boundaries of tri-knowledge, offering insights that benefit fields as diverse as developmental biology, dermatology, and forensic science.